Yes, so welcome everyone to the fifth talk of the fifth season of the Isogeny Club. Today we have the one and only Riccardo Invernizzi giving his talk. He's a PhD student at KU Leuven, and he's gonna talk to us about PRISM. So the floor is yours, Riccardo. Go ahead.
Thank you, Jonathan. Thank you to the organizers for having me here. And thank you everyone for being here and listening to me. So today I will present a recent construction called PRISM from prime degree isogeny mechanism. As the title suggests, we'll use prime degree isogenies to construct some schemes that I will present. So let's start from the beginning. First of all, I should give some credits that I didn't put in the first slide because, as you see, there are many people involved in this, but I think it's important to mention them all. So we have Andrea Basso, Giacomo Borin, Wouter Kastrick, Maria Cortreal Santos, our co-host, me, then Luciano Maino, Anton Aldru, Frederick Verkauteren, and Benjamin Wesolowski. So yeah, a lot of people, big collective effort. Now let's go to the main idea of the scheme. So as I mentioned, the scheme, our scheme use high degree isogenies, and the main idea is that compute such isogeny is very hard if you don't know the endomorphism ring of a curve. So you start from a curve, you want to compute a high prime degree isogeny, and if you don't have the endomorphism ring of such curve, the best way you have is to use points, do value kind of thing. But these algorithms are exponential in the smallest prime factor of your degrees. In particular, if the degree is prime, is exponential in the degree of the isogeny. However, if you know the endomorphism ring of this of your starting curve, then you can look at everything on the ideal side. And as we know, on the ideal side, everything is much faster, and we have recent tools to compute isogenies starting from essentially every ideal. And this is very nice, and this is also fast, and this is exactly what we want in crypto. So we have a trapdoor, we have a secret object that is, in this case, the endomorphism ring of a curve, and with that we can compute something efficiently. Without that, we cannot compute something efficiently, and actually it's exponential time to compute such a thing. So this is really a good cryptographical setup. So from this we can make an identification protocol. I should add a disclaimer here. So in the literature, there are some like a bit of discussion of what an identification protocol is or isn't. So for this discussion, we will just make it very easy and very simple. And today an identification protocol will just be something that I have, and I can be queried. And if I'm queried, I can prove that I own my identity. So in this case, the identity is going to be the endomorphism ring. We have a verification key. That is what we usually call a public key in public key cryptography. And this is a random curve that we call EVK. Then we have a secret key. And as I said, this is my identity. So the secret key is the endomorphism of this curve, or equivalently, or almost equivalently, the ideal of a secret isogeny that we call ISK. And this secret isogeny is the isogeny that starts from E0, which is a prescribed curve, to our secret curve. And then the query that I receive is a big prime number. We denote it Q through all this presentation. And to prove that I really own my identity, so that I am really myself, I respond with a degree Q times 2 to the A minus Q isogeny starting from EVK. So it is clear that if I don't have knowledge of the endomorphism ring of EVK, I cannot compute that, because as we just said, the cost of computing such an isogeny is exponential in the biggest prime degree, which is Q. However, if I have it, I can compute it. And so if I produce such an isogeny, it means that I am myself and I know the endomorphism ring. And to verify, one just have to evaluate this isogeny that I produce it in interpolation form. So I produce a way for the verifier to evaluate it efficiently. And then the verifier can check the degree and check that I really know an isogeny of such a degree. We will get into the details a bit more later, but this is the main idea. And this can be turned into a signature scheme or vice versa. Like the two concepts are very similar in this case. In a signature scheme, we have a public key, and this is the random curve, the secret key. And as I said, this is the connecting ideal and or the endomorphism ring of the secret key. And the query in this case, we don't have a query, we have a message, what we have to sign. And so we start from a message and we have to hash it into a prime number. And that's the main difference. And I will also talk more about that in a moment. The signature is, again, once we get the prime number Q, is a degree Q times 2 to the A minus Q isogeny starting from EVK, and the verification works exactly in the same way as for the identification scheme. Okay, so let's get a bit more into the details of how we can do it. First of all, we have to generate a secret key. This thing is now done in many different protocols in the same way. This is the higher dimensional way of computing secret key. And we usually start from E0. As I said, E0 is like the well-known curve of which we know the endomorphism ring. And so it's very nice to start from there, because every time we compute an isogeny from there, then we can bring the knowledge of the endomorphism ring to the new curve, which is exactly what we want. Then we have two main ways to generate the secret key, which is essentially just an isogeny. We have the heuristic key generation, and this is from an idea from QFESTA that start by computing an endomorphism of degree n times 2 to the a minus n on E0, and that we can do since we have I on E0. That makes very easy to work with. Very easy to work with endomorphism. We know the endomorphism ring, but also it is very, very easy to work in that. So we can find endomorphisms there efficiently. We compute it, and then we can split it using isogeny factorization. So every time we have an isogeny that has two factors that sum to a power of 2, or that sum to a power of any other number that you're comfortable with computing higher dimensional isogenies, we can split in the two parts. So we can write a Canny diagram, and we can recover each of the two parts with that. So we have an endomorphism of degree n times 2 to the a minus n. We split it in two. We get, we take, let's say, the n part of it, and we have a degree n isogeny that goes from E0 to another curve. And this curve will be our public key. The same thing, we can do it more rigorously using a method from SkiSign to the West, which is also a bit slower, but ensures that the public key is uniform among all the possible curves that we can land on. So we first sample uniformly random ideal, and then we apply the ideal to isogeny procedure that I will also talk a bit more about, but essentially translate an ideal into an isogeny and then allows you to evaluate the isogeny. So that's exactly what we want. But in general, any other method that gives us a curve and the endomorphism ring of that curve is good for us. So that's really what we are interested in. An important remark is that such method should not consume two torsion, because we are really interested in the two torsion. This will be clear in a moment. So these two methods are very good because we can generate an odd degree isogeny. So n can be odd, can be prime, can be essentially anything that doesn't involve two. And we are very happy with that. So these two methods are quite fast, quite efficient, and they are very good. In practice, we will choose the second one in our implementation, but the first one is like a bit less secure, a bit faster. That's just a choice. Then we move into the response. So we got in both protocols, let's say for the signature scheme, we actually get a message and we turn it into prime. We assume it. We assume we already turned it into prime. So Now we have a prime number Q, and we want to generate an isogeny of degree Q times 2 to the A minus Q. So we work again on E0, and we generate an O0 ideal that we call I challenge. And this will have norm Q times 2 to the A minus Q. And this we can do again with a random fixed norm ideal. That is the same routine that we use to do the rigorous key generation. Then we can compute the push forward of this ideal through the secret key. So we know the secret isogeny, we know the ideal associated to the secret isogeny, and we can compute the push forward of this ideal through that ideal. Then we take the ideal I sigma times I secret key. This ideal starts from E0, and this is very important because ideal to isogeny works only on E0. So this ideal starts from E0, goes to the secret key, and then goes to a new curve. But the new curve, the path from the public key to the new curve has degree Q times 2 to the A minus Q because it corresponds to the ideal I challenge that we pushed forward. So we translate it into an isogeny. Then we recover the last part of the isogeny because we know the secret part of it, so we can remove it. And then finally, once we are able to evaluate this isogeny sigma, we evaluate it on the two torsion. And then we, instead of sending the image of the two torsion bases of the public key, we send the torsion scaled by a factor, Q to the minus 1. And we will immediately see why that is the case. But before, let's talk a little bit about this ideal to isogeny algorithm that we are using. This is an algorithm from SkiSign to the West that, as I said, turns every ideal into an isogeny, or say almost every ideal into an isogeny. And it works by taking the ideal I, finding two equivalence ideal, I1 and I2. And these two ideal will have norm D1 and D2. And then once we have a pair of random ideals, we try to find integers u and v such that d1u plus d2v is 2 to the a, so this is a power of 2. If we find such ideals and such numbers, then we can build a canny square using I1 and I2, and this square allows us to recover I. Now, we don't really need to know much more than that. We can just use this as a black box, but this algorithm has one big requirement, and the requirement is that it needs all the possible two torsion available. And by this, I really mean that for a size of P, we need access to a two torsion that is close to P. It's like very close to P. So for this, we need the P to be of the form F2 to the A minus 1 with F a small cofactor. And also we are really interested in not wasting two torsion. That is also why I said before, like the secret isogeny, we want it to be odd and these kind of things, because we really need almost all the two torsion to be available for this, or all the two torsion to be available. But on top of that, we have no other requirements, and we can reuse the SkiSign to the West parameters. Those parameters have the same requirement because the scheme heavily used this ideal to isogeny algorithm, and they are also optimized for a lot of fast arithmetics, point computations, and things like that. So those parameters are quite good, and we can just reuse them because we have the exact same requirements. And then the other step that we were missing is how do we hash into a prime? So this only holds for the signature, of course, but we get a message and we want to hash it into a prime number. So how do we do that? We take any cryptographic hash function that hashes 0, 1 into the set of numbers between 2 to the a minus 1 and 2 to the a, where a is going to be defined later, but this is our two torsion. We compute the hash of the curve, we attach the message, we attach the counter. So the counter starts from 0, and then we check if we find a prime. And if we didn't find a prime, we increment the counter, we check again, and we go on like this. So by the prime number theorem, we know that primes are 1 every log n. So in particular, we expect 1 hit every A attempts. Every hash computation, well, computing the hash is extremely fast, but after hashing, we need to check if the number we land on is a prime. And this has a quadratic complexity, but in A, so it's still okay. But once we find it, so we look for it while signing, then we find it, and then the counter, we can attach it to the signature. So the signature is going to be the image points that we discussed before, plus this counter, because when the verifier have to check, otherwise they need to redo this process again. But if we send the counter, then they can just immediately compute the hash, because they already know the one that is gonna be good. So that's not a huge saving, but quite a saving and for no cost. So we just decide to include the counter in the signature. And finally, verification. So as I said, from the message and the counter, we can immediately recover Q, and then recall that we don't send immediately the image of the points that we get, but the image scaled by Q to the -1. And in this way, the kernel that gets sent to the verifier, which is PVK, so basis on the two torsion on the public key, and the P signature, which is the image scaled by Q to the -1, that's immediately the kernel of a two-dimensional isogeny. This two-dimensional isogeny is the one that factors our big isogeny sigma. So sigma has degree Q times 2 to the A Q. The isogeny with this kernel splits it into a component of degree Q and a component of degree 2 to the A Q. So the verifier doesn't have to do anything, just takes the point, compute the isogeny. This isogeny embeds the two factors of sigma. And then the verifier only need to compute it on this like P prime PVK0 and get P prime something else. And this is going to be like one component. So it encodes either the degree Q or the degree 2 to the A Q part. And then they can just check with the pairings. And if the pairings match, so it's either Q or 2 to the A Q, which modulo 2 to the A is just -Q, then we are sure that we sent to the verifier a degree Q isogeny, because the degree Q isogeny is embedded in this two-dimensional isogeny. So it means we know it. So this is the verification. And yeah, so now we can talk a little bit about the security. So what are the possible attacks against the scheme? First of all, we need a little bit of discussion about high degree isogeny oracles. So this is now a very hot topic, I would say, because many higher dimensional schemes to prove security rely on what they call high degree isogeny oracles. And this started with SkiSign HD, sorry. And they do that because without such oracles, it's hard to argue security. Because in the security games, you need to simulate transcripts, and those transcripts are done by someone that's not doing the actual protocol. So you usually need someone to simulate a high degree isogeny. The first thing that they mention when they use these oracles is that there is no known way to compute such curves without an oracle. So they need the oracle because there is no other way, which is what half of our security claim. Like there is really no way of computing a high degree isogeny. And they also claim that giving such an oracle does not harm the security, because such an oracle does not leak information, which is the other half of our security claim. The reasoning behind this is that smooth isogenies already cover the isogeny graph. And so if you get a high degree isogeny, that is something like you could compute a high degree isogeny yourself, just a smooth one, and that would essentially give the same information, apart from the fact that a high degree isogeny is even harder to use because you cannot find the kernel, you cannot do much. So there is no reason to believe that revealing such an isogeny leaks information. So we already reach what we can call security by common belief. Like we have an assumption, but it seems that everybody believes that is a hard assumption. Another bit like of far-fetched security discussion is that since those schemes rely on isogeny oracles, on high degree isogeny oracles, if someone breaks one of their schemes, like if ski sign to the west get broken, it means that it cannot exist an isogeny oracle for high degree isogeny. So it cannot exist something that produces these isogenies. So it's very unlikely that someone can break our scheme, right? Because if someone can break our scheme, then can produce an isogeny oracle that makes their scheme secure, and vice versa. So it seems that the security assumption that they do is a bit complementary to what we do. So if such an oracle exists, then of course our scheme is broken, but their scheme is secure. And if it doesn't exist, or if their scheme is broken, then it doesn't exist and our scheme is secure. Of course, this is not rigorous mathematical proof. There are many things in between that can go wrong, but let's say high level, at least one of the ski sign HD mechanism and our mechanism should be secure. And yeah, so now let's look a little bit more in detail into the concrete attacks that can be done. Key recovery is really the usual thing. So you need to compute the endomorphism ring of a curve. We argue that this curve is a random curve. Again, we use the ski sign to the west uniform key generation for this reason. So we can argue in the same way that we expect that curve to be random. The best known algorithms are collision finding kind of algorithms. And they require P to be roughly 2 lambda for a security level of, or require log P to be 2 lambda for a security level of lambda bits. So this is, again, very standard. We can, again, use the same parameters as ski sign to the west, for instance, because they have the same security limit. But now we go to what is our actual problem, which is computing a high degree isogeny. So I've been telling you that this is hard through the whole talk, but how hard is it actually? So the problem is, I give you a prime number, a big prime number Q, and I ask you to compute a degree Q times 2 to the A minus Q isogeny from a given curve, EVK, for which you don't know anything. So it turns out that the best way to do that is using the Velou square root algorithm. The Velou square root algorithm is a very nice way of computing isogenies, and it works in complexity square root of Q, as the name suggests. But the problem with this is that it works in complexity square root of Q on the extension where the Q torsion is defined. And this extension is going to be O of Q. Again, so the total complexity is roughly Q to the 3 half. There are other ways, of course, of computing isogeny, but they blow up quite fast. They are this is the only method that we know, or that we think is currently known, that even reaches the complexity of Q to the 3 over 2. So we need the Q to be bigger than 2 to the 2 lambda over 3. And so A, which is the 2 torsion that we're going to use, to be greater than 2 lambda over 3. But if we go back a little bit, we know that to prevent endomorphism ring recovery, we need P to be 2 to the 2 lambda. And then to use ideal to isogeny, we need P to be P minus 1 to be essentially done by only 2 torsion. So we have the 2 lambda torsion available, the 2 to the 2 lambda torsion available So 2 lambda over 3 is like way below this limit. So we don't need to impose extra conditions. We are already fine. For level 1, we need A to be 90 bits. So computing a 90-bit isogeny is 128-bit hard. So for this, we are completely fine. There are a couple of more things to take care of. One can reuse a signature. Well, not reuse the entire signature because then you have to find the same message. But one can be tempted to reuse a part of a signature. So we know that our signature has degree q times 2 to the a minus q. This means that we give away all the factors, well, the factor q and all the factors of 2 to the a minus q. As I told you before, any isogeny can be factored in polynomial time. Of course, that's not efficient. That may require to go through dimension 4 or dimension 8 isogeny computations, which are not at all practical, but of course, an attacker doesn't have to be practical. It just needs polynomial time and is very happy with it. So we can really factor the 2 to the a minus q isogeny and take all the small factor out of it. And then we may say, okay, so did I gain something? Can I reuse maybe a big factor of 2 to the a minus q somewhere else? But then we just choose q to be bigger than 2 to the a minus 1. And so this will never help because the prime can never land into the set of primes that we can see, because 2 to the a minus q will always be lower than 2 to the a minus 1. So in these factors, we can never get a q that we will use. And since the complexity of the isogeny computation is dominated by computing a q degree isogeny, if we don't see the q degree isogeny, we don't gain anything. And so just hashing into numbers bigger than 2 to the a minus 1 prevents that kind of attack. And then there is the other observation that we already made before, that the actual problem is not given q, compute q times 2 to the a minus q isogeny, but given q and q1 2 to the a minus q1 isogeny, q2 2 to the a minus q2 isogenies, and so on. So given many signature, compute a new one. So the question is, does seeing all the past isogeny help into computing a new one? But we already argued that this should not be the case. So the last thing that we have to look at is hashing. The last attack that one may do is looking for hash collision. So we hash into primes. How expensive it is to find two messages that hash into the same prime. At the first sight, it seems that since we hash into less primes, so the hash space is smaller, then finding collision is easier. But actually, this is not the case, because it's true that we hash into a smaller set, but hashing takes longer. And so this is a technique that is already used in other protocols, that is called repeated hashing, where you make the hash more expensive to increase the cost of finding collision. But in our case, it has like a very simple explanation. You're not actually hashing into the set of primes, you are really hashing into the set of numbers. And then you hash into some numbers, and at some point you find a prime, and only that one is good. So it means that you are hashing into the set of numbers, and you have to find a collision which is prime. So this is actually harder than finding a collision normally. So normally a collision would ask would require A to be roughly 2 lambda. In this case, well, we have the fact that the collision have to be prime, but we don't even take that into account. Another thing that we can take into account that has a bigger impact is that for each hash that we do, we also need to do a primality testing. And that has a cost. So our hashing is really more expensive than doing a single hash. So we can slightly increase the value of A. And for instance, we can take A to be 219 for 128 instead of 260 that would be. So we can gain a little bit there. But still, this is by far the biggest constraint we have on A, because As I said, like the size of Q, so the hardness of computing an isogeny, would just ask us for A to be 90 bits, and now we immediately jump to 219. So this is really the big difference between the signature scheme and the identification scheme. In the identification scheme, the query is Q. So I give you a prime, you give me the proof that you own your identity. And for that, we are okay with 90-bit primes. But for the signature, to protect against collision finding, we have to ask this isogeny to be of degree 219. So 2 to the 219. So here we really lose a lot, but we didn't find a way around it. So that is really what is expensive in our signature. So now let's compare it a little bit with other isogeny-based signatures. We know that there are many of those. The biggest family is the ski sign family, which is based on a completely different paradigm. So we use prime degree isogeny, they use Fiat Shamir that we don't have. What we have is kind of a Hessian sign thing, which again, I put it in blue because in the literature, Hessian sign mean different things. For us, it's simply you get a message, you hash it into prime number, and then you sign the prime number. So it's very simple. We expect it to be much more flexible. So it should be much easier to construct new schemes on top of this scheme because it's very simple. It doesn't require much. While for ski sign, it's really not the case. We know ski sign have been around for quite many years already, and there are no many advanced construction based on it. We have an example from this season of the Isogeny Club, actually. That is the presentation that Giacomo gave about Erebor and Durian, which are ring signatures built on top of ski sign. But that was also quite difficult, so they had to tweak a little bit the protocol. It's a very interesting paper. I recommend to go and read it, but they really had to tweak the protocol to build something on top of it. We expect our to be much more flexible due to its nature. And this comes at no expense in size and speed. And this we will really see that we are as efficient, if not more efficient than most of these schemes, and as compact again. So we really hope that this flexibility is going to give us a lot in the long run. However, I have to mention that we're not the first prime degree isogeny-based signature, because there was previously an idea from Anton Alleroux that constructed a verifiable random function called Düring VRF that is also based on prime degree isogenies. And then we have ski prime, which is a high-dimensional variant of ski sign based on the Düring VRF. So let's look at how they work. The idea is to pick a prime, compute the basis of that prime, the rational basis of that prime, and compute a basis of that torsion such that there is an endomorphism known that sends one point into the other. And together with this, you can compute the ideal associated to the isogeny with kernel the single point. And then it's easy to compute the ideal associated to the point P plus KQ. And then this ideal can be evaluated again with ideal to isogeny. In the Düring VRF, K is just the input of the function, and the output is the codomain of the isogeny. In ski prime, K is the challenge that cannot be computed by the verifier. So the verifier just sends this K, and that is evaluated by completing the diagram. So that doesn't use the ideal to isogeny, but it's more ski sign-like mechanism. So yeah, it's really a bit different. They focus more on the ideal. So to compare it, the big difference is that the VRF requires a fixed prime. So they generate high prime degree isogeny, but for one prime and many isogeny, all the rational isogenies that are there. In our case, we look for different primes. Every isogeny has a different prime degree. To have the D torsion rational, they need D to divide P plus 1, with D being a big prime. Again, this imposes a condition on P, which in turn makes harder to generate a P of the form f2 to the a minus 1. So this cofactor that you have in your prime is going to be bigger, and this impacts ideal to isogeny. I know it's a bit complicated to follow, but it's really like there are little things that go all together. But the fact that you have less to torsion make ideal to isogeny is lower and harder. The rest is mostly the same. Hessian sign and verification, like Hessian sign also works the same, and verifying, you get the isogeny, you verify it. But for those things that I mentioned before, PRISM is faster than the During VRF in all steps. So key generation, signing, and verification. ASCII prime, as I said, is not really comparable in this sense because it's the high dimensional the high degree isogenies are really used in a different way. So that's a bit more different. So now let's get to concrete implementation and the performance of our scheme. We will start from sizes. So the public key, we can remember that we work over fp squared, and p is 2 lambda bits. So a curve is just one Montgomery coefficient that is 4 lambda bits. Then we need to send the deterministic basis of the public curve that we publish. However, well, this can be either included, so we have to send the points, and this is going to be faster because the verifier doesn't have to recompute it every time. But of course, it uses a lot of space. Or we can compute it on the fly, and this is way more compact because we don't send a point, but we spend more time computing the basis. There is a cool trade-off that we can do between these two things, is that to send hints to generate these bases. And this is, again, a trick from SkiSign to dWest, but I think it was known even before, even maybe in the original SkiSign. Anyway, we can give hints to compute a deterministic basis, and this comes at basically no cost. It's like 2 bits or something like 2 bytes or something like that, and gives us significant speed up. So in the end, we also go for that idea. Then the signature. So again, the codomain is 4 bits, 4 lambda bits, 1 Montgomery coefficients, but now points. Points will need 2. The x and the y, they are both in fp squared. So we pay 8 lambda bits per point, which is a lot because if we need to send a kernel, that's 16 lambda bits. Now we can do deterministic basis and get two coefficients per points instead of 2, like the x and the y, and the 2 coefficients, those are 2 lambda bits each. So we can get to 4 lambda bits for a point. But in total, this makes 12 lambda bits. And we are now asking the verifier to compute the deterministic basis of the image curve. If we ask them even more, we can only give 3 coefficients and recover the fourth one with pairings. And we can get down to 11 lambda bits. But as you see, this starts being quite expensive. Instead, what we can do is to send the 1 point. We fully send 1 point. That's 8 lambda bits. But from 1 point, we can recover the Montgomery coefficient of the curve that we are looking at. So this requires only 1 field inversion. And then we send the x of the second point. That's 4 lambda more bits, and 1 more because we need to tell if the point has a positive or negative coordinate. In this way, we only pay 12 lambda bits, and we don't need to compute the deterministic basis or the pairings. So this is much faster than the previous way and has essentially the same cost. So 12 lambda bits instead of like the 11 very compressed in the other way. So this is the better way to do it, and that's what we do. And this is a comparison with the other schemes that I promised you before. Well, SkiSign, in the beginning, it had 11 lambda roughly. SkiSign to the east is also 12 lambda. Can go to 10 lambda bit, but it's also much more complicated and need more 2D steps. ski sign to the west is 9 lambda, can go to 8, but then is a similar trade-off of what we had before. And ski prime has 19 lambda, can go to 12 lambda, but using 4-dimensional isogenies, which are entirely not practical. So as you can see, this is really like the same size. And also we really don't want to push the size, because compared with other post-quantum schemes, being short is always going to be a big point for us. So 12 lambda, 10 lambda doesn't matter much, because that's what we do good with isogenies. It's much more important to save some computational time, which is the choice of all these schemes and also of our scheme. Another interesting thing is the communication cost for the identification scheme. So as I said, the problem is really that in the signature scheme, we need to prevent hash collision. In the identification scheme, we don't have this problem at all. So we only require A to be lambda plus log lambda, because that's what we need for Q. That's the size we need for Q. The curve is still 4 lambda bits, but now the points, we can send them as coefficient. So yeah, here we need the deterministic basis, but we gain a lot, because the size of the two torsion is no longer 2 lambda, but is lambda plus log lambda. So essentially lambda. So 4 points cost us 4 times A, 4 coefficients of size A, which is 4 lambda plus 4 log lambda. And if we compress them, we even get to 3 lambda plus 3 log lambda. So the total cost is 8 lambda or 7 lambda, which is much better than the other scheme, than the signature. The signature is 12 lambda. So if we compress everything, we can get to almost half of it. So that's, again, really the difference between signature and identification scheme. We can already see it from here. And then we can go to the performance. This ugly table shows all the isogenies divided by degree that we need to do. And you see our scheme just does, this is for the signature scheme. We only do 2 isogenies. We don't have 1-dimensional isogenies. And you can see from the numbers that signing is 500 isogenies, while for West is 1,000. And verification is 200 instead of 126 for ski sign West. But both signing and verification in ski sign West require 248 dimension 2 isogenies. We add the fact that we have 2 hash, but hash is very, very cheap, and we do 64 roughly primality testing in the signing, but 64 primality testing against 250 2 degree 2 isogenies. I think we can still do better than that, and the number of isogenies that we have is really half of it. So this already tells us that this should be quite faster than ski sign to the West. With East, the comparison is a bit closer. We know that East is faster than West. We don't have concrete implementation, but estimated to be faster than West, but a little bit less secure. But still, we have less 2 isogenies than ski sign East in the signature, and also we don't have degree 2 1-dimensional isogenies that they also have in East. So we see that we can perform slightly better. Yeah, and this is, as I said, we don't have the commitment and the challenge for people that are a bit familiar with ski sign. We don't have the other half of the diagram. They need to compute it at some point. So that's really good for us. We pay because we have to hash, and our hashing is a bit, it takes a bit of time, but that's like 1 or 2% of the signature time. So it's really not a big impact. And PRISM ID, so the identification scheme version, is almost twice as fast. And that is the same as as with the signature size, because the verifier only has to compute a much shorter isogeny. So the size of the isogeny of the verifier depends on the degree Q that we are allowed to take. And for the signature, we need 2 lambda. For the identification scheme, we need lambda. So the verifier will have to do much less work. and it's going to be almost twice as fast. So that would be impressive, but for the signature, we don't have a way to get around the hash. So this hash is really our bottleneck. The isogeny computation is not the bottleneck here. The isogeny security, not the isogeny computation, of course. The hash security is the bottleneck and not the isogeny security. Anyway, we implemented this using the SkiSign to the West code base. So most of the algorithms are the same. And as you can see, the timings really reflect what we see. So we have key generation that is the same, so it takes the same time. Verification is a bit slower. Signing is now 1.8 times faster, but currently we have a bugged version of the or not bugged, but like not really optimized LLL. The LLL should not essentially not take time, and right now it takes 40% of the time. So we don't expect a reduction of by 40%, but we can expect to have still a bit to gain. But yeah, already now we really take much less than SkiSign to the West in signing and slightly more in the verification. And for the other scheme, again, we see that this really shows that what we see in the diagram with the isogeny computation, it's really close to what happens in practice. So we can estimate that way, and yeah, and we have the same estimates that we've seen before. So to conclude, what we have is a scheme that is totally different from most of the traditional scheme, let's say the SkiSign based ones. It has competitive performances and sizes, but is much more flexible, much more simple. And so it's more open for future construction and for future constructions, and eventually maybe more optimizations that we also hope. That's it. Thank you all for your attention, and now I will leave the floor to questions.
Thank you very much for a great talk, Riccardo. Sorry. Yeah, as always, if anyone has any questions, just type them in the chat or unmute yourself and ask them. I thought the results were super impressive. It looks really cool. Great protocol. So I was wondering if I don't know if probably there's no clear attack like this, but did you consider the type of attack where you see a bunch of signatures and then you're asked to and the attacker is asked to try and come up with a new public key that can somehow use these signatures that you have seen to generate new fake signatures?
Well, if the attacker, somehow if such an attack exists, then an attacker on this new curve can sign everything, right? Because he can also generate a curve by himself and then start signing messages and then do whatever attack to move all the signature you want to this new curve. So I think that the question is really if you fix the other curve, so if you fix the other curve that the attacker can use, then I think you go back to the end ring problem, because you can fix the curve to be E0 and then you can build it. Otherwise, if the attacker is allowed to choose the new curve,
I mean, if they're allowed to choose a new curve, I agree with.
Then then they
can just compute it as a regular public, but it has to be somehow fixed. So.
Yeah, I think so.
Yeah, good point.
So it seems much faster than signature. Do you have applications in mind where it could be useful? Yes, so it can be useful in situations where you need an identification scheme. So now I'm not really a security protocol guy, but I think most of the kind of digital identity kind of things. It can be very useful there. You have the problem that most of the times when you just want to identify, you are usually interested in something that has low power consumption, so that you can, I don't know, can embed into a smart card or whatever. So embedding 2D isogeny computations in a smart card, I think it's gonna take some time in the future, but yeah, I don't know, if you're just interested in proving that you have your own identity, that's the kind of application that we're looking for now. More than these, which, as I said, may probably not be a place where people would look for isogenies. I don't have any other immediate concrete idea in mind, but this is a very general problem, like identifying yourself digitally and securely. It's a very general problem. So I think in the future we may see one of these contexts in which having short signatures can be really important. And on top of that, as I said, this is like really flexible. So this would require even more imagination, but I'm quite confident that it can happen that you have a bigger protocol, and as a subset of this bigger protocol, you need to identify yourself. And then you have this identification scheme, which is very nice, very fast, and also very compact. And yeah, and I think that is gonna be where it can really be useful, like as a block for bigger schemes. I think for how it's done, it's really very simple. You hash into prime and you compute the prime. That can really be helpful. So that is my hope, but also my belief, I would say.
Mark also has a question, I think, so you can unmute yourself if you want.
Great, thank you. Yeah, I just missed a little bit at the start how you generate public keys, because you presented there was like 3 points, and it sounded like you said that you were going for the third option.
No. We go for the second option. Sorry if I said that. We do the rigorous key generation. The third option can be useful, again, if we want to do more advanced protocols where you may have some requirement on the kind of torsion that you have, or things like this. And in that case, it may be, or like the secret isogeny have to have a specific form. And I think we discussed kind of things like this. In that case, it can be helpful to generate it in other ways. But for the standard protocol as it is, we just go with the rigorous key generation of ski sign west.
Okay, then I was just confused. So, but okay, thank you.
Thanks.
Is it possible to have a link for PDF version of this paper?
Sorry?
I would like to have a link for a PDF version of this paper.
Yes. So the ePrint is coming out soon. Is not out yet, but it's gonna be out in days, I guess. So it's gonna be available soon.
Okay, thanks.
Okay, nice. If there are no more questions, then thank you again for a very nice talk, Riccardo.
Thanks.
And then in 2 weeks, it will be the last Isogeny Club talk of this season, and then we will have Sina giving her talk, Sina Scheffler. So stay tuned for that. And yeah, thanks for today.
Thank you.